Welcome back. It's a pleasure to introduce Siddhartha Gadgil. Siddhartha Gadgil is a faculty member in the mathematics department. Just a little bit about him. He's actually ultra local. He grew up on campus and went to ISI to do his BStat and then subsequently to Caltech to do his PhD there. And then after a brief stint at the Indian Statistical Institute as an assistant professor, he has come to IISc and he's been with us since about 2005 or 2006. So Siddharth is going to speak about alpha geometry and friends. So just a little bit of background about how this talk came about in this reinforcement learning conference. In August 2022, Siddharth said, Rajesh, I'm teaching this particular course, which is on automated theorem proving. We have been having discussions on and off at the faculty club and various places where how can we automate theorem proving? What kind of techniques can one come up with and so on. And in August 2022, he actually taught a course where he was doing all of these things in a systematic way, teaching students how to automate mathematics. But one aspect when I was attending those series of lectures that I noticed at that time was that it was very good at testing proofs, but there seemed to be a lack of creativity in the set of proofs that were being generated because it was using a database of proofs, converted proofs that people had written. So they were all human based. So where is this creative element coming from? And when you actually look at the way we do proofs, there is a creative aspect with errors. And then we correct those errors using methods, which were the kind that he was doing in his August 2022 class. And then came a revolution where there was generative AI. And today's talk is actually his explorations in this domain. And we look forward to listening to you, Siddharth, on how to automate mathematics.
Thanks, Rajesh. Thanks very much for the introduction and the opportunity to speak about this. So this talk was motivated by work from Google DeepMind. I'll talk very little about my own work on called alpha geometry. I'll start with talking about that, but also about friends. So it was in fact an email conversation with Rajesh which prompted this talk. So I'll talk about alpha geometry, but I will also talk about the general patterns which are common between alpha geometry and other systems, and about how AI for mathematics can be done. I'm not going to be comprehensive. This talk is not a survey or an introduction. It's rather an invitation to this very growing field. So to start, sorry, can this light be reduced a bit? I think the screen is not very visible. Thank you. So I'll start with something really elementary, just because for this audience, but just because we want to fix some common examples. So here are a couple of common examples of proofs. Okay, sum of angles of a triangle. Well, you know that it's 180 degrees, but how is this? So consider a triangle, and the key step ABC, and the key step is to draw a line through A parallel to BC. Okay, and now you can see that interior opposite angles, these two blue angles are equal, and the two red angles are equal, and the sum of the three angles at A is 180 degrees or pi. Hence, the sum of the three angles of triangle is also 180. Okay, so the picture and the proof is from Wikipedia. So another elementary proof, and again a very old proof, that there are infinitely many primes. This is equivalent to showing for any n, we show there is a prime P such that P is greater than n. Okay, and the key idea is to consider the number n factorial. I'm sorry, this Chrome is misbehaving here, but I hope the slides will be okay anyway. So we consider the number n factorial, where we all know what n factorial is. Sorry, consider the number n factorial plus 1. And let P be the smallest prime factorial of n factorial plus 1. Okay.
You want to go out of the presentation mode, that might be better.
Yeah, well, I don't know. It was fine before this Zoom started. Okay. Let's hope others. I think it's math jacks. There's not much maths. It's only the math jacks that's misbehaving. Okay, so let me just say it in words. You pick the smallest prime factorial of n factorial plus 1. And if this number is less than n, then it divides n factorial. So it cannot divide n factorial plus 1. So it's a prime greater than n. Okay, so those were two concrete examples. My point is to make some general points which are very well known. The reasoning or proving has two components. There is intuition, which is based on analogies, associations, etc. So they are used for these auxiliary constructions like drawing that line or considering n factorial plus 1 or even considering the smallest prime factor, which theorem or definition to use. And in more complex proofs, what are the intermediate steps? What are the intermediate lemmas? There are not rules that tell you these are based on intuition. And then there is logical or algorithmic component, which are the deductions and computations. Intuition is based on tacit knowledge, that is things that we know but can't tell, like riding a bicycle or swimming. And this is acquired by learning through experience. Perhaps you have to learn it through experience because these are high Kolmogorov complexity. That's irrelevant for the rest of this talk. And a counterintuitive fact, which is related to what's called a Moravec paradox, is in raw computation power, intuition is actually much harder. Okay, Moravec was mainly talking about sensory motor tasks, but including vision and so on. So we tend to think of logic as harder and intuition as easier. But by an objective measure, which is computational power, intuition is very hard, which is why the intuition side of reasoning did not exist really till little more than 10 years ago, because there wasn't good enough hardware. No, so this is a rough sketch. So this is just a rough sketch and there's no precise thing. So Daniel Kahneman has something called system 1, system 2, which is commonly had. So intuition is system 1 and logical is system 2. It's not well defined, but roughly we all understand what it means. It's a general sense. Okay, so with this background, let me come to the actual first star system, alpha geometry. This is a remarkable system. It's an AI level system that can solve geometric problems. Okay, and more precisely, it can't solve all of them. You have to write them in a particular language, in a symbolic way. And it can solve those geometric problems which can be expressed in this language. 75% of the Maths Olympiad geometry problems can be expressed in this language. So it can only attempt those problems. But very remarkably, and this is the first system that handles these kinds of creative, intuitive problems at skill level, it manages to solve these problems. If you look at its scores on these problems only and compare it with people who wrote those, its average score in these problems is between the average score of all the silver medalists and gold medalists. In fact, it's very close to the gold medalists. It's a little below a gold medal quality in IMO, which is way above me, for example, and above most people. So what's alpha geometry? It's a few weeks ago. Yeah. So this is a very fast moving field. This is a paper in, I forget, Nature or Science from Google Research, actually. Google didn't mind, but Google Research Hub. It was a few weeks ago, and it's, yeah. Yeah. I don't know off the top of my head. You mean geometry problem which can't be? No, I don't actually know. I shouldn't say off the top of my head. Yeah. So I'll say something about the language, but I don't know. It's a very fixed language. Okay, so how does this system come about? And this is related to the pattern I said earlier. There is one component of this, which is what they call a deductive database plus algebraic reasoning to chase down ratios. This is a powerful and efficient deductive system for reasoning about geometry problems. This is extending earlier work. You can say the work has been all 70 years of computer science is building towards this. Data structures, algorithms, symbolic AI. So your better and better way of deducing things. Okay, but these are fixed finite deductions that you can make. They increase efficiency on previous work, but this is a continuous flow. And a language model that suggests the auxiliary constructions, like drawing that line, or in other contexts, you would say n factorial plus 1, but we don't yet have things in other contexts. So in geometry, the auxiliary constructions, there are no rules to tell them, and there aren't good systems of rules. You use a language model. The third component is the most important, which is, well, I said language model, and I'm not going to explain them. We'll treat them as black boxes. Where do you get data to train it? You could take existing problems, but there are hardly any. So the biggest contribution of the people doing this work was the generation of synthetic data to train the language model. In fact, this is what took the most computational effort. I will say what this synthetic data is and how they generate it. So the crucial point is you have a pair, the intuitive system and the rule-based system, algorithmic system, and you generate data. So you have to extract or generate data to train the intuitive system, and a lot of it. Okay, so first, what is the deductive database plus AI? So in the deductive database, you have efficiently represented a finite collection of points and relation between points, lines through them, etc. For example, per ABCD says the line through AB is perpendicular to the line through CD. Okay, so there are 10 to 15 such relations. Some are dependent on others, so I can't say precisely what they have. And rules of deduction let us deduce consequences of these. This is open source, fortunately, so you can just check. There are 43 rules of deduction that are there in alpha geometry. In addition, something is telling you that, say, perpendicular is symmetric and transitive, but the explicit rules of deduction are this. For example, if AB and CD are both perpendicular to BC, then they are parallel to each other. This is one of the rules of deduction. I mean, there are a bunch of rules of deduction of these form. Okay. And what the deductive database does is by iterating deduction with all the rules that apply, you get more and more consequences. At some point, you stop getting new consequences, so you stop. So for a fixed finite set of points, you don't add new points here, but you can deduce everything which you can deduce without adding new points. With the rules of, yeah. Yeah, they're fed as axioms. They're treated as axioms by this system. It's a domain-specific system, so it's not embedded in a larger logic, but they are the axioms of this. Exactly. And there is one more side of this, which is the algebraic reasoning for chasing ratios and so on. So alpha geometry deduces from algebraic relations for angles, lengths, and ratios. They all turn out to be of this form, A plus B, C plus D, and so you can represent them in matrix and use Gaussian elimination. So one of their contributions is improving the DDAR, the deduction engine, to make it fast. The improvement is important because synthetic data uses these millions of times. Okay, and now the main contribution. Where did they? Yeah.
Can you explain this chasing ratios idea?
No, so just that in geometry proofs, you often have this plus this by this is this by this and so on, and you have to reduce using that.
But
yeah,
it was a sum.
So if it's a ratio, you take the log. If it's angles, you take the sum. But from the rules of deduction, any relation they get can be written in this form: A plus B, C plus D. Yeah, thanks. So I didn't say that. Thanks. Ratios you can't. It won't be a sum of ratios. It will usually be a sum of the logs of the ratios for which you have the relation. And using that, you can deduce with efficient. That's all. This is really an efficiency gain, not a fundamental gain. So the synthetic data. How do you get data to train the language model here? So you take millions of random configurations of points. Here a configuration means a finite set of points and a bunch of relations between them. So for any, you choose how many upper and parallel and this and that. Okay, so millions of these. And then all the theorems were deduced from the initial configuration. They found 100 million theorems. For each of these 100 million, you traced back to the minimal proof. Fine, so far so good. But now this is what we always say in mathematics. What is a non-trivial theorem in mathematics or any applied mathematics as well? It's where the proof contains something that the statement did not. So in this particular case, if the proof contains a point and the statement did not, then you have to have an auxiliary construction introducing that point. And these auxiliary constructions are known. Okay. And then a language model is trained on this. I'm going to treat these as black boxes, as I said. In fact, pre-trained on all proofs for those who know, and fine-tuned to predict auxiliary constructions. So there were two phases of training. Okay, so this is what we did. Just to clarify this, no IMO problem was exactly as such in the synthetic data. So there was no copying the full solution. Yeah.
So these deductions
yes.
were not with that previous deductive system.
It was exactly with the previous.
These involve addition of points.
No, so you threw away points. Thanks. So I should clarify that. So you have a theorem. So you started with 15 points. Maybe you started with 5 points and some relations between them. And you reduced all theorems. It turned out that some theorem statement involved only 4 of those 5 points, but the proof involved all 5 points. In which case it becomes a statement about those 4 points, and the construction of the 5th point is an auxiliary construction. Yeah, so thanks for the question. That's the clear point. That is you created the whole proof and then just observed that this point was never used in the statement but used in the proof. So we have to introduce it with an auxiliary construction. So the same deductive system can give you synthetic data. These are the key ideas which generalize to many contexts, but key ideas in this system. So given these, how does the system work? Yeah. Yeah.
So you have the theorem statement, but, and a proof, and there is something that's extra. But, which one? Here you're starting with random configuration, and then deducing something.
Yeah.
There. So how do you select which one ought to be a starting point theorem that you want to?
No, so you have a statement of a theorem, and that statement of the theorem involves certain relations. This is perpendicular to this. This is this thing, and so and so. And you just note what points are present in that statement. Just purely what is part of the logical statement, logic in this restricted logical sense.
So all of this should extend beyond geometry.
Oh, yes. All these principles extend everywhere beyond mathematics in some sense. I mean, this principle that you can use a deductive system to generate synthetic data and use that to train an intuitive. That's the point of this alpha geometry and friends. The general principles are very general. And that's why I meant, yeah.
Can you please explain what we mean by no IMO?
It just means that they generated synthetic random configurations. Just by chance, they may have generated exactly a problem that appeared in an international maths Olympiad. They post-checked with their data and found that did not happen. If that happened, you will worry about contamination, that it has learned from that. If it happened only in one problem, you would exclude that or something like that. As it turned out, there was no contamination.
Two points.
Random
configurations, how are they generated?
That I don't know. Yeah. So some of these details, actually, they're not even in the paper. Okay. So some of these details you have to look at the paper, and some other details I've looked at the paper and looked at the code, and even asked the authors on Zulip, and I still don't know. Okay, so some of these things are not documented anywhere. They have some sketch in their paper, but I don't know exactly what is the distribution, for example. But if I'm not mistaken, that level of detail is not even in the papers. It's not just that I don't know, but it's not even known, obviously. Yeah.
So the each configuration,
Yeah.
multiple theorems.
Yes, yes. They got lots of theorems. So you trace every theorem.
So you trace every possible theorem and then
For every configuration. So it's not per configuration that you're doing it, but per theorem. You generate configurations and you generate theorems. But once you have generated them, it's the theorem that is important. Yeah. Yeah.
The theorem is a set of points.
No, so every theorem is a series of deductions which starts with some assumptions that these points are parallel, these are perpendicular. It uses the rules of deduction and concludes that something is true. I'll soon give an example that will make things clearer. Yeah. The language model is pre-trained, as I said, on all proofs in the language, and then it's fine-tuned for the task of predicting auxiliary constructions. There are 71 possible auxiliary constructions, which is already part of the language. Yeah. Again, some of these details I don't know, and some of these details are not even public. So, some it's my fault that I don't know, some are not even in the paper. Yeah.
go back one slide where you written how the theorems are used.
I'll come to an example. Maybe we can return to this, but because these things are clearer with examples, I have an example slide, which from their paper. Yeah. Okay, so how are the problems solved? So it's just the next slide, not forward. So given a geometric problem represented symbolically, that is some things perpendicular and so on, all deductions are made using this. And if they solve the problem, wonderful. And a few IMO problems they actually solve. Even older systems solve. But if they don't include the auxiliary conclusion, then the language model is asked to suggest candidate auxiliary constructions if they don't include the final conclusion. And for some or all of the auxiliary constructions, suppose we pretend only one auxiliary construction is suggested, you make that and then you make deductions based on that. And you keep repeating this process. In practice, so if you assume that at each step one auxiliary construction is suggested, then you make the construction, deduce everything, make the next one, deduce everything. In practice, it suggests a collection of them with weights. And so you have to do some kind of search. What they do is they use what's called a beam search. They actually experimented and said it's quite robust under the nature of the search. So I won't go into any details of this, one, because this is kind of classical, this kind of searches in computer science, and two, they themselves say that's not important. So as I said, the language model is important, DDAR is important, but the most important is the synthetic data. Okay, so here are two pictures. This will, I hope, clarify things. Here is the simple problem they say. Let ABC be a triangle with AB equals AC. Prove that angle ABC is BCA. They try to deduce and you won't succeed in deducing anything from this. Until you make that crucial construction. You take B to be the midpoint of BC. So you add the midpoint of BC. And then you drop the line AD. Well, you don't actually drop the line because any 2 points have a line in their language. But what you do is you add the midpoint. And note that when you add the midpoint, you get BD and BC as a consequence, and BCD are collinear as a consequence. So any auxiliary construction comes with the consequences. It says this is a point and this point has these properties. Okay. So now once you make this auxiliary construction, it is easy to deduce these two triangles are congruent from the hypothesis, and this angle is equal to this angle. So one auxiliary construction, it deduces from there on. This is the system. And here is an IMO 2015 problem 3. It involves 3 different auxiliary constructions. All these examples were midpoints, but as I said, there are 71 different auxiliary constructions. There are lots of them. 3 different midpoint constructions and a whole bunch of deduction. So this, yeah.
Does it only produce proofs which are already known?
No, all these are, well, has it discovered a new theorem in mathematics? No, it hasn't. But we don't generally try to discover new theorems in Euclidean geometry. So that's, I think, the main reason. I think it has no inherent limitations. So within its domain, IMO problems are probably the hardest problems any human is trying. No human is doing research on Euclidean geometry. So it's a very important question. Is it discovering new mathematics? And I talk about other systems that do discover less powerful, but they do discover new theorems. But here I feel one reason it cannot discover new theorems is exactly because nobody actually does. It's not an active area of research. Euclidean geometry.
So the auxiliary construction could also be bisect the angle A.
Yes. Yes. You have circles, in circles, and so on. As I said, there are 71 of them. I open the code. I won't open the code now and see, but it's open source, so you just have to read.
Even for an existing theorem, there could be new proofs.
Yes, that's right. I don't know. I don't know if it found new proofs of the IMO problems or every problem some candidate or the other had found. Yeah.
So just to understand, these are the proofs given by alpha.
Yes. This picture, yes, both of these are exactly given by alpha. Incidentally, it's a remarkably lightweight system because after this thing, it runs on this, my laptop even. It can actually run on a laptop and not just this, it can give some non-trivial theorems there. I don't know if it can run the bigger theorems on laptop, but yeah, because the model is only some 300 million parameters. It's not a large language model. I mean, yes, today you'll not even call it tiny, you'll call it micro or something. Yeah.
If you get that last line, it says about 109 steps.
Yes.
Is this step language or improved language very verbose or?
No, I think that's because IMO problems are hard.
That long?
Yeah. I mean, yeah.
Just to make sure, does it come with a guarantee that this group is?
Yes, assuming you trust the axiom system. So they're using a bespoke axiom system. They did talk about this, and I will mention these things. You would rather want it to embed in first order logic or an interactive system that you trust, but they just used it. So if you trust that their reduction system is correct and their auxiliary, so they make auxiliary constructions. They're just saying we are going to construct a point with this property. Maybe that's impossible. So if you trust the reduction system, these proofs are. No, it cannot be higher. I mean, it's suggesting auxiliary constructions. So I assume that some of the auxiliary constructions will be useless. And it is possible that hallucinations in the sense that auxiliary constructions may have invalid syntax, in which case you just reject them. So the great thing about passing through a deductive system is that there are no hallucinations that escape the deductive system. You just throw them away. So the only hallucination you could have here is something suggesting making an auxiliary construction which doesn't exist. And I would guess that it does make such things which are simply rejected. Again, it's not something that is mentioned anywhere in the paper, so I cannot other than guess. Yeah.
So I would rather take an example from the first.
Yeah.
So in the first problem, where an isosceles triangle. Would the language model suggest construct a midpoint of BC?
Yes.
Or would it suggest construct a midpoint BC such as the following two?
No. It suggests construct midpoint BC. The first line is what is the language of the thing. And in a certain file in the thing, it says that midpoint DC has these properties. Yeah, thanks. So, yeah.
When it fails, you ask the question.
I don't know. Again, you can experiment. It's open source. What happens? And also, it's you see the two systems are decoupled, so you can only run the language model part again and again. Are there problems where it deadlocks? What happens if you? I don't know. It probably fails. Otherwise, they would raise their rate by. If there's a simple fix, they would raise their rate. But more details than that, I don't know. Okay. So let's get to friends. This is a section I'm going to skip except for assignment. So the last component I didn't talk about, which is large language models, and I'm going to treat them as a black box, just except for mentioning what abilities they have. So they have remarkable abilities, roughly corresponding to intuition. They can reason by analogy, and very importantly, compositional analogy, not just a simple analogy that this is this. But many components are analogous to different things. They can mix and match. So compositional analogy or compositional generalization is one of their superpowers, and the other superpower is natural language. Because natural language not only makes interaction with them easy, it makes them have access to our human literature as well. And that is crucial in these cases. They are familiar with a lot of stuff, but they can also combine broad knowledge with specific knowledge from their input. What is called in-context prompting. Yeah.
Natural languages come with their own ambiguity.
Right.
So how much of that affects or?
Yeah, so that's why they hallucinate. That's why they sometimes get things wrong. So it's not perfect at any of these things, but it has roughly, I'd say, almost human level natural language ability. So but they can handle it rather well. So yeah, but they are terrible at avoiding logical fallacies and judging correctness. This is the weakness here. Okay.
Avoiding.
Huh?
You mean avoiding logical fallacies?
Yeah, they're terrible at avoiding logical fallacies. They tend to output things which are logically rubbish, and they cannot look back at their solution and tell whether it's correct or not. I'll come to that. So this is their big weakness. They have many strengths. So pairing them with deduction and checking systems is the natural way to build things. And many systems, as you see, even alpha geometry is built on that. Okay, so I'll move to more examples. Okay, so here is a new mathematics result, not terribly interesting mathematics result, but a new result called the CAPSTACK problem, which was solved by fun search. So there is the CAPSTACK problem is to find the largest possible set of vectors in this finite field Z0 tree to the n, a vector space over this finite field, so that no three vectors come to 0. So geometrically, it's like taking the points at 3 points by 3 points by 3.7, n equals 3, and choosing a set of points so there are no lines. Okay. This is an important problem, and apparently Derrida called it a favorite problem and so on. It's a much studied problem in extremal combinatorics. So exact results. So you could try to approach this by brutal enumeration, but up to n equals 6 only we have exact results, and beyond that neither theory has given the best result, nor has, and brutal enumeration cannot go beyond this. But a system called Fun Search from Google DeepMind found the construction for n equals 8, which was the best construction. So this is a new mathematical result. As a result, it's a new lower bound on the size of this set. It's an explicit construction.
When you say best has it so far?
Best so far. Beat the record so far by a fairly big margin. So best so far. Yeah, it doesn't mean it's provably optimal. In fact, it's not, so far as we know. Now, the interesting thing about this, again, like alpha geometry, a very generalizable system, it did not find the CAPSTACK. Instead, it found a program to find this set. Okay, I'll be a little more precise. It did not, so it does a evolutionary search. It's an old idea. Okay, but in fact, most of the program for generating CAPSTACks is fixed. It's what's called a greedy algorithm. You pick a point, then you pick what looks like the next best point to add, and so on. Keep adding the best point you can. Best based on a function which is called a priority function. And this priority function is learned. So it's learned by evolution. At any, you start with one handwritten priority function based on what somebody thinks is a good idea. And at each side, we have a population of such functions. We evaluate these functions, choose the best, and combine to get new functions. This is an old idea. It's used for traveling salesmen and so on. But when you're using a usual evolutionary algorithm, what do you mean by combining? It's easy to combine parts, words, etc. How do you combine functions that you can't do normally? But this is one of the powers of the language model. So you use a language model. This is Cody from the Palm 2 family. This is the previous best, not the Gemini from Google. Their code-directed thing. You give it instructions and you give it example functions, and it generates a new program. Of course, some of those will be worse than the original, and some of those will even be wrong. But this is a way in which you can evolve things by hand. Okay. Indeed, as you see, this method is entirely general, and they did use it to solve some other more practical optimization. You can try to generate, have an evolutionary algorithm to search for basically anything using this philosophy. Another which I like a lot, which I think is maybe most practically useful, symbolic integration, finding the integral of sine x plus cos square x or whatever else you do. This is work of Lampel and Francois Charton. Charton has a lot of very nice videos and papers about these and related things. So language model was trained to symbolically integrate a given function. Again, same story. You want synthetic data. And there are three forms in which they generated. First is you cheat. You know, Mathematica is rather good at it. Just get it to generate random functions and try to get it to integrate. If you have got it, you have got it. Okay. But then the result will still be better than Mathematica raw. But this is not very generalizable because it depends on existing systems being good. More interestingly, we know that integration is the reverse of differentiation. So you randomly generate a function and differentiate it, and then you know integral of f. This one can do, and it's very nice. The problem is that distribution is a little bad, in that you tend to have short functions with long integrals, when in practice what you got is a relatively short function whose integral is long, and that's why you could not find it. Okay, and these people have a really nice idea to do it synthetically, which is called backward generation with integration by parts, which I'll explain. So you pick random functions capital F and capital G, compute their derivatives little f and little g. Do it at a stage where you have already done a bunch of backward differentiation. Now, if little f times g is already in the training data, then we know it's integration, integral. Okay, that is because little f times g is you use backward or something to generate it, and then you can compute the integral of capital F times g by integration by parts. And then we find that the distribution you get if you do backward generation and then do backward generation with IBP is of the correct nature. Because this is often a longer function, the integral than the left-hand side. So you get synthetic data with which you can train this. Okay. They have used similar approaches for all sorts of things, solving ODEs, solving recurrences, and so on. The general principle here is you're often solving in mathematics inverse problems where the direct problem is easy. Solve the direct problem with randomization to generate synthetic data, and then you have a train your model. This is yeah.
When you say these functions with the correct distribution of function field, right? Is this a mathematical statement or is it
no, they're actually calculated distribution. I think it's roughly uniform. I don't know the exact details, but no, they're not eyeballing. They calculated the frequency, the length or whatever frequencies of the two sides. I am reporting a qualitative statement they made. I haven't looked at the quantitative data, but the authors did look at it quantitatively. So, yeah. Yeah.
So in that case, what is the meaning of short functions?
Short just means when you write it on paper or in a computer, it's short. So that's okay. So I'll have to make a little bit of a digression now. So we have looked at some systems before going to the new ones. Yeah.
So based on the rules of deduction, or there's also some construction that?
No. So here these two did not use any real rules of deduction, just computation. Yeah. So symbolic algebra, not numerical computation, but just symbolic algebra. So that's the point. Thanks. So that brings up to the new thing. So if you look at these three systems, one of them used a restricted rule of deduction just for geometry, and the other two did not really use deduction at all. They just used symbolic algebra. Okay. One used computation.
These are three different things, so not part of alpha geometry.
No, these are the friends of alpha geometry and friends. Yeah. So I'll be not talking more about alpha geometry. I was talking about various systems of doing things. Okay, so these use rather specific things. What if you want to do general mathematics? One way is SAT solvers, and also their more general counterparts, SMT solvers. Just to point out, so SAT is the original NP complete problem. It is given finitely many Boolean variables, true or false. Can you solve them? And you have equations involving these. Can you find the solution for this? So Cook-Levin theorem, any problem in NP can be reduced to SAT. But the important point is in practice, lots and lots of problems can be reduced to SAT. So the clever idea computer scientists have developed is that you map lots and lots of problems to one problem and work hard at solving this problem very, very well. This works very well in practice. One mathematical example is this Boolean Pythagorean triples problem. It was stated in the 80s by, okay, I'm forgetting for a moment. But it was stated in the 80s and solved a few years ago, in 1916 or so. It is, can you color the integers in two colors, red and black or red and blue, so that if you have a triple like 3, 4, 5, which are three sides of a right angle triangle, or 12, 5s, 13, then they cannot all three be the same color. It was found that up to 7,500 or so you can, and beyond that you can't with a SAT solver. These are examples of these. This is more general logic, but this still works for only finite problems. For general problems, you have resolution theorem provers. They involve this thing called unification, where you find correct substitution. They can solve problems in first order logic. And first order logic is in principle all of mathematics. In practice, these solvers work only if the proof depends on a small number of axioms. But that's still a powerful system. So one example here is Robin's conjecture. This was a characterization of Boolean algebras, that is the structure of true and false, in terms of commutativity of the OR operation and one single equation. So it's a commutativity and associativity of OR, and this equation gives you all the other properties of a Boolean algebra. This was conjectured in 1930s. Okay, and Tarski students worked on it and so on. So it was considered an important enough problem for many decades. It was solved in 1996, William McCune's automated theorem prover EQP. Now, some of the ideas of this, like discriminant trees and so on, are still heavily used in the interactive theorem provers. I'll come to next. So in practice, first order logic is very poor for representing a large body of mathematics. For those in more computer science background, that's why you have scripting languages, you would say, as against something like OOP or whatever else. Managing complexity is different from local reasoning. So first order logic is very good for local reasoning, in principle for everything, but in practice, no. What you use are interactive theorem provers, software systems where proofs are obtained by human machine collaboration. So the computer both finds proofs and verifies correctness. And with these, mathematics can be digitized on a large scale. In particular, lean theorem prover is the one that is heavily used in mathematics. Its library includes most of undergraduate mathematics and now many advanced topics, including many theorems proved just a few weeks ago and so on. So what is the value of this? There are many uses of these, but one is they can give you a superhuman level of correctness. The one issue is, why are you trusting these interactive theorem provers? You don't have to trust the whole theorem prover. The part that checks the proof is called a kernel. It's a small amount of code, hopefully well documented, and it's all open source anyway in today's era. So the analogy here, which is a bit of an oversimplification, is chess engines are huge programs, but the part that checks what is a legal move is a much smaller program. So that has to be correct so that for all the moves to be legal. So similarly, checking this. And even better, Leo de Moura, Lean's creator, is very particular about these things. Even better, you can write your own proof checker, an independent kernel. As of today, with Lean 4, there are 2 other kernels written in Lean, and then one more written from scratch in Rust. So there is a completely different kernel which checks your proofs. So there is really, you can trust these proofs. And if you really are paranoid, write your own kernel. Okay. But in addition to correctness, which we really don't care that much about because nobody died there because the theorem was wrong, there are other benefits from this, which is collaboration does not require trust between collaborators. So mathematical collaboration is limited because somebody gives you a proof, you have to check whether it's correct unless you really trust that person. And it also means people with local knowledge can't use it because things are often stated slightly wrong and they will prove things correctly. And we can even collaborate with knowledgeable, imaginative experts whose proof we absolutely cannot trust, like large language models such as GPT-4. I wasn't about to insult someone. Okay, so now I'll turn to some other systems involving interactive theorem provers. The draft, sketch, and proof, which came about a year ago, it gives formal proofs, that is, proof which can be checked by a computer. You give it a statement, it does it, and the way it does it is it uses a large language model to generate an informal sketch of the proof. It's translated into a series of steps so that the problem is broken into sub-problems. Concretely, the proof was written as a series of statements in Isabelle. They used Isabelle, not Lean, because it has better automation as of today. So what you did is it gave a proof, it wrote it as a series of statements, and used rule-based automation to complete the proofs. This is a typical pattern. And it had decent success rate with high school mathematics problems. What if you want to go to a larger scale proof? Well, you can try to translate. At this point, I'm being speculative, but it's kind of obvious what you would want to do. You can try to do it iteratively. That is, translate step by step. Where it fails, you can backtrack. And to do this, you would want to translate to structured proofs. You may want to add details. You can put knowledge in the prompt, which works very well with language models. You can guide using heuristics, etc. For this to work, you need two things, and I'll give demos of GPT-4 doing these things to different degrees of success. One is you need translation to formal systems to have high accuracy, because you're going from an informal to a formal proof. And the proof generation by language model itself has to be good. If you do that, you can hope you'll generate an informal proof, which is going to have a lot of rubbish, but you will keep checking it and feedback and iteratively improve things. Oh, okay. So here's a demo of the translation part. This is a system of myself with a bunch of collaborators, including Anand here. This is lean, except that I'm typing in English, because let's say I don't know how to write. There are infinitely many natural numbers. It has started working now. And the language model, it goes to GPT-4. Language model suggests the translation where you can replace it. This is, of course, a much less impressive system than what I said, but I can tell you the insights of the system. Okay, so this is a system we call Lean. How do you get good responses from GPT or 4 or whatever else from a language model? So suppose we are given the statement of a theorem. We find, let's say, 20 statements that are similar to it. And these are documentation strings in the library. So we already know their translations. And we include them in the prompt. And then we query GPT-4 and ask for a bunch of responses. And then we discard responses that are not valid. This is like a question of hallucination. So there will be hallucination. You throw away things that are not valid. And because Lean is a very strict language, generally if things are valid, the chance they are correct is reasonably high. Okay? These are not so easy to fake. So here's an example of a prompt. If a vector space is two-dimensional, then it's finite dimensional. This is only an excerpt from the prompt. You give a system prompt, and then I say the user said this, and the assistant replied this way. These are examples. I give 20 such examples. Finally, I said the user said this, and you as assistant, please reply to me. And the assistant replied by translating it into English. This is quite a complex statement, actually, but it manages fine. So these were one of 40 silly statements we used. We used a bunch of silly statements to test. But when you test, you're always worried about contamination. Has it already seen this somewhere in the literature? Well, you can be pretty sure nobody in the literature is going to write a proof that if a space is two-dimensional, then it's finite dimensional. It's far too silly to do this. So this was one of the tricks we had. We also had 40 theorems and 40 false statements in our test set. Originally, we used codex. When we went to GPT-4, we found a certain phenomenon. We had to exclude from our results a few statements, because when we asked it to translate 40 some of these false statements, GPT-4 just said these are false instead of translating them. So anyway, out of these 120 examples, we had success rate of 85%. These were relatively simple. So it shows that translation can work, at least in simple cases. Okay, so how can we try to improve it? However, this success rate was below 50% for proof method. And there are many causes of failure, typically notation, but one that I did not guess till I actually looked very carefully at the examples and failures. So this proofnet standard, it took the problem from Rudin, and Rudin perversely uses the term condensation point, where more reasonable people will call it accumulation point or limit point. And MATLib indeed uses accumulation point. This means prompts go wrong. Okay, so we need to translate. So this has to be corrected. Or we also need to translate statements whose translation is not a single statement but a block. Okay. And so I go to my final part. I'll be a little brief here. So we can address all these issues using GPT-4 for auxiliary tasks. And this is the last set of slides. I'll be quicker than I intended for this. GPT-4 examples, just to show you here. So suppose we want to correct the fact that something uses condensation points. I can ask GPT-4 to tell me all the mathematical terms and tell me all the synonyms. And then look up in the library and find I have had the terms in the library. So I look up in the library and find that the library uses accumulation point, it doesn't use condense point. So get GPT-4 to translate. Okay, so these are examples of when you think of using it, you don't think of one shot getting the answers from the language model. You break up into lots of tasks and lots of auxiliary tasks it does really well. Okay, here's another example which I will go through very quickly. So this is code in lean code which I wrote as part of my own course. It finds the smallest element in a list which is non-empty and proves two properties of it. That's it's in the list and it's less than or equal to the elements in the list. Okay. One thing about this is, and I just asked it to describe no examples. This is what's called zero star. And it says it defines a function and two theorems. It gives a correct description of the statement and it also gives a correct description of the theorems. So this is again a task it does very well. Just in case you thought GPT-4 only copies, this is clearly not the case. This won't be anywhere. Right there. Okay, so now quickly some examples. So I asked it some simple linear algebra problems. This one it gave 3 solutions. Interestingly, 3 different solutions. Can ignore this. Then I asked it this problem, and I was a bit embarrassed when it told me that I formulated it wrong. It gave a counter example. Then I formulated correctly a somewhat non-trivial problem. You take a square matrix, prove that if A cube is I, then A is diagonalizable. If you don't understand, this is the sort of thing we'll ask incoming PhD students. And GPT-4 answered. And indeed, I was talking to friends, and friend Shona pointed out, this is something we really had asked our incoming PhD students. And anyone who answered was selected. Find all 2 by 2 matrices with rational entries such that A to the 5 is I. This is a mix of linear algebra and some number theory. And indeed, GPT-4 gave a 2 by 2 matrix. And it started by noting the minimal polynomial, the degree of the minimal polynomial, and then verified these things. And then I realized that as I would with a student, it had used a non-trivial fact. So I said, you use this, prove it, and proved it also. So it's pretty impressive in these cases, but not so impressive in other cases. I asked an analysis question, which I had again asked incoming PhD students. And based on this answer, I asked a simpler question. And it persistently gave wrong answers, even though I tried to guide it. And it kept trying to use every increasing sequence is unbounded, which is false, or assume the maximum is attained, which is also false. It kept using these. Okay? But if you asked it to prove or disprove, it gave a counter example. So it knows it's false, it still uses it. This is what I mean by it really doesn't try to be logically consistent. Interestingly, another model, Mistral Medium, was much better at such questions. But overall, I think GPT-4 is still better. So as part of the reason I think it's so bad at these analysis questions is so many people, especially in America, are forced to take calculus courses. There's just a lot of garbage on the internet. Yeah. A side point is smaller models work for auxiliary tasks. Here's another example, and I won't go into any details of this. Let me just point out though, in its third solution, in fairness to it, it proved by contradiction saying that something must be 4, but it is 4, therefore so and so. So when I said it's terrible at judging correctness, I don't think I've met a student yet who gives a proof by contradiction based on 4 is not equal to 4. So it can be very impressive, but it can give garbage. You have to filter out and do. Couple of other auxiliary tasks it does very well. This one I found in the wild. Actual statement from a paper of mine with exposition about meta-Abelian groups. I said, due to lack of time, I won't say much, but just if you want to see the slides later, you can see them. The slides are on the internet, but it managed to give details very well. This is important if you're trying to automatically translate from mathematical text, which may be at high level, to lean or something like this. In fact, I was quite impressed with, I thought I would have to give it examples, but with no zero shots, it picked up all sorts of subtleties. It messed up this formula, but if you do it iteratively, it would probably get it correctly. And another auxiliary task, we would want, and when I say iteratively, step by step, what are the steps? You would want some kind of structure to it. So I realized that maybe the best way, instead of teaching it a structured language, is go with a language it knows very well. Those who are familiar with computer science will recognize. This is JSON, of course. I tell it that everything is, every state, make a list. Every element in the list is either an assumption, observation, theorem, or an assertion. An assertion has a claim and justification and what it uses. And it can do this very well. So these are all the ingredients that are there. So with this tour of many things, let me summarize. Language models can be used for many core and auxiliary tasks due to these abilities, but due to their unreliability, it's natural to combine them with effective tools. Comment here, this book I was reading by Andreas Wagner, who's an evolutionary biologist. So a more general lesson, are they creative? So a definition widely used among psychologists apparently of creativity is finding original and appropriate solutions to a problem. Language models try to find an appropriate solution. They are certainly original. They are, however, they try to find appropriate by analogy and so on, but they are very poor judges of appropriateness. So they can match creativity provided a problem is either easy enough or the notion of appropriate, like poetry, is flexible enough. But with a filtering by a deductive system, maybe you can get the both parts of creativity. The last comment I'll make is, while we are talking about automating mathematics, really what we want in the shorter term is to combine AI, language models, or whatever next form comes, interactive theorem provers, and symbolic algebra, Mathematica, Sage, etc., to actually make tools for discovery, formalization, and learning of mathematics. We don't just want to keep working for 10 years from now or 100 years from now when things get automated. We want to help people on the 3 to 5 year time scale, let us say. I think that is reasonable. So I like with my last thank you slide, which is my wish list or to-do list of things that can be worked on. Okay, but I won't go into it.
Thank you, Siddharth. For the audience, actually every one of Siddharth's lectures in his class are like this, intense and fast. And you have to be really on your toes to be able to catch what he's saying. So over to you all now for the questions.
So it's very non-uniform depending on the area. Partly based on who is on what is easier or harder to formalize, and partly based on, but mostly based on who has got into the business. So on the algebraic side, enormous amount has been formalized because perfectoid spaces are formalized. This is made a level of work and everything building up to that. On the other hand, algebraic topology is only now being formalized. Probabilities and analysis, particularly complex analysis, are getting much better. So it's highly uneven. In some areas of mathematics, it's gone well beyond the first year. And in other areas, it is lagging. So one of the tricks used is you have a grand challenge, you formalize this or that. And everything that's to the background gets automatically formalized. So sphere eversion was a graph, using H principles was a grand challenge, that was achieved. So differential topology is formalized, but not that much Riemannian geometry. Complex analysis is a little complex analysis. Terry Tao is leading an effort to prove the prime number theorem and a bunch of other such results in analytical number theory. Terry Tao and Alex Kontorovich, I should say. And so that means over the next few months, a lot of it will get formalized. Yeah.
So
Yeah.
the example of when you say compensation.
Right.
A similar example is, I think, this eigenvalue.
Yeah.
It says characteristic.
Yeah.
So is there, can we say have a dictionary of sorts,
Right.
thesaurus of sorts?
Right.
Does that?
Yes, you could try to build it up. What I actually did in advance, and by the way, I should thank Microsoft for that. It's because of funding from my cloud credits from Microsoft, not funding in any other sense, that I could run so much on GPT-4. So what I did in advance is I took every documentation string, 40,000 of them, and told me what are the mathematical terms in this. Okay. So now you give me a statement which involves condensation point. It fails to translate. Then I can extract condensation point and all the synonyms and look for those synonyms in this pre-built list. So what you are saying is, can we build a dictionary of thesaurus? We can try to do that. I could also ask it in advance to build synonyms, but it's more efficient to have one half, the database half, done in advance, which I've already done, and the other on the fly. Yeah. Yeah, but in general, that's a very good process. So what I've done is sort of, yeah. Yeah. Yeah, no, so language models, the good thing is they're really no natural language, in the sense that they pick up things from context. Usually they will, if you ask it correctly, the same term is used with very different meanings in group theory and topology, knows which term is that the context is topology or this is even with common language where you have the same word. In particular, it has no problem telling apart the mathematical term being used technically and the ordinary English word being used in the same way. Yeah, so that's not. Yeah.
So, can the proofs made by, say, one search explain what it is? Once we combine all those.
Right. So that's actually a very interesting question, and in fact, this was done in the sense that fun search went. I skipped to that because I was going through many things. They actually had multiple iterations of fun search. They found the configurations that it was generating, found they had a certain symmetry to them, added that symmetry to the generating program, and reran it. So since it's a little bit of Python code and not modest amount, whatever, 50, 60 lines, because it's only one function of Python code, a person can read it. And it was actually read, and on the basis of the nature of that, it was improved as well. So yes, certainly. So that is one of the things about these proofs. So the SAT solver proofs are enormous. No human can really read them. The proof of the Robbins conjecture is medium in size. It's 12 pages or something like that. Somebody printed it out. So different systems, somebody wrote it in a human readable form, and a virtuoso algebraist could have found it, or logician could have found it. So some of these proofs, especially those which are LLM generated and so on, are actually very much readable once you find them posteriorly.
Let's thank Siddharth once again for this. Oh, we have a gift for you as well. Okay. That I think you probably have a copy of this book yourself.
Oh, no, I don't. I don't.
And coffee.
Oh, thanks a lot. Hello.
Thank you. Thanks a lot. Thank you. Your talk. Your talk. You just wait for the promotion. We have one more talk. I'll request those who are leaving to stay a little silent and exit. Yeah, next talk is by Abhishek Ghosh. Abhishek Ghosh is an assistant professor at IIT Bombay, at SysCon and C-Mines at IIT Bombay. He's actually one of our own graduates. He got his master's from the Electrical Communication Engineering Department at IISc. Then subsequently, he got his PhD at Berkeley, and then was a postdoc at UC San Diego before coming to IIT Bombay. He's going to speak about banditry. And over to you, Abhishek. Welcome back to IISc. Thanks. Yes.
Hello. So I understand that this is the last talk, so I will act accordingly. I'll let you go early if I manage to finish. So as mentioned, I'll be talking about computing bandits in non-stationary matching markets, and this is one of the works in a sequence of works with Abhishek Kannan, Tara, and Arya. So let's begin. So little outline. So I will just pose the matching markets problem, you will very soon see what the matching market problem is as a multi-agent, multi-armed bandits, and then we'll talk about collision in such a system and how to resolve those collision. And finally, we'll talk about this dynamic markets, which is the main theme of this talk. And we'll propose algorithms to deal with non-stationary markets, and we'll give the solution, some theoretical as well as some empirical results. So that's the outline. So what is the matching market? So typically, in economics, they design a matching market as a bipartite graph, where in one side you have the demand side or the agent side, and the other side is typically the supply side or the arm side. And the goal here is to find the optimal bipartite matching. I will going to explain what that is in the presence of competition. Why competition? Because you have multiple resources and multiple agents. So it's possible that more than one agents can go for a particular resource. So there might be competition in the system. And I must say that this has received a lot of interest in recent years, in the last couple of years or so. And it's been popularized by mostly by Mike Jordan and his group at Berkeley. And there's some nice works in this field recently. And these are basically motivated by these labor markets, online labor markets like TaskRabbit, Upwork, and also this Mechanical Turk, this crowdsourcing platforms like that. And so some classical motivation of this kind of matching comes from this very old Gill-Shipley stable marriage algorithm. And also some, like in US, they kind of match these medical interns and residents to their hospitals and all by this kind of matching problem. And the idea is to find what's called a stable matching between the agents and the armed side. And we'll want some additional property on top of being that a stable match. Okay, so we'll explain all these terms subsequently. Okay, so how do we model this kind of bipartite matching? So we kind of say that each agent has a preference over the arm side, and each arm has a preference over the agent side. Okay, so now if I know these preferences, then I can simply run Gill-Shipley stable marriage algorithm. So we teach this in undergraduate, how to do these things, and it spits out a stable match. Now, the crux of this particular problem is that we don't know these preferences. Okay, and suppose in some applications you are given a choice to successively interact between agents and arms. So now the idea is, can we use some successive interaction strategy between these agents and the arms to learn these preferences and then infer from that? Okay, so one model is via bandits. So what the exact model is the following. Suppose we consider n agents and k arms, and we assume that when a particular agent pulls a particular arm, it receives some stochastic reward with some mean. So this is the standard assumption in multi-arm bandits, right? So I can treat agent i's preference as the ordering of this arm means. So that's the standard multi-arm bandit framework. You want to pull the arm which is the highest mean again and again, right? So if I look at just the action of agent I, it's simply a multi-arm bandit problem, right? Now, this entire problem can be thought as multi-agent multi-arm bandit because you have multiple agents. Okay, so the main idea is one can use tools from bandit literature. One can use algorithms like UCB. One can use algorithms like explore and then commit to address these kind of problems. Okay, but there is an issue here. So the issue is that of competition. How do we resolve conflict between multiple agents when they are going for a particular path? So this is not like I'm solving any different multi-arm bandit problem. You need to solve them in the presence of some sort of competition. Okay, so in order to do that, I will make like simplistic assumptions one by one, which people typically do as well. So one such assumption is what's called one-sided learning. So it's typically assumed that the ranking of the agents are actually known to the armed side. So we started with the problem saying that we don't know these preferences in both sides. Now I'm bringing this two-sided learning problem in one-sided, where I'm assuming that the ranking of the agents are unknown to the arms. Okay, so this is called one-sided learning, and this so people kind of motivate this by example. So in clinical talk, or also you can come up with an example, or more classically in college admissions, these agents represent colleges, and the ranking of the colleges, these are some sort of a common knowledge that's available. So it's not unreasonable to have a one-sided learning framework, although we want to remove this as well. So now, how do we deal with collision? So if more than one agents pull a particular arm, then the reward will be given to the agent whose rank is highest among the candidates who are colliding. Okay, so that agent is given the full reward, and all the other agents will receive a deterministic zero reward. Okay, so this is how we resolve the collision. And for this, you need the knowledge of this ranking, right? Otherwise, if two agents collide on a particular arm, then arms actually need to know the ranking because they want to resolve this conflict. Okay, so that's the simple one-sided learning and conflict resolution framework people typically use in this framework in this area. So we can make one simplistic assumption, although this is not necessary, but this will provide me with benchmark to characterize the performance of my algorithm, aka regrade. We'll look at it later. So people typically assume that the preference of the agents, so that is same for all the arms. So we started with a very generic case where this preference can change based on each arm. Now I'm saying that I assume this one-sided learning, and I'm also assuming the case where this ranking is fixed for all the arms.
The college ranking,
yeah,
isn't it like this?
Yes, so that's the example where the ranking is independent of the person who is looking, right? So this is called a serial dictatorship model. And as Professor Sundaran said, that this college ranking falls in one of the applications. But this is rather strong. But we'll soon see that this will give you a benchmark to characterize regrade. Okay, so let's look at the regrade, and let's look at this one-sided learning and this global ranking or serial dictatorship model. And without loss of generality, assume that agent J is ranked J. So agent 1 is the highest ranked agent, agent N is the least ranked. Let's look, so under these conditions, one can show that the stable matching is unique. Okay, and the unique stable matching is given by the following. So the agent 1, who is the highest ranked agent, so that agent will pull the arm of its choice. Okay, since it's ranked highest, it doesn't care about other agents. But suppose think of agent 2. If it pulls the arm that is preferred by agent 1, it will get deterministic zero reward, right? Because of the conflict resolution strategy. So it will just avoid the arm preferred by the top agent. So similarly, agent rank R will delete the arms preferred by the agents ranked higher than it, and it will pull the best from the rest. Okay, so that's the strategy, and you can actually show that this forms a stable match, and this stable match is the unique stable match under these two assumptions. Okay, so one can minimize a regrade with respect to this unique stable match because your algorithm will output a matching, right? So in terms of formulations, if I'm playing algorithm A and it is playing some arm LJ, I can characterize how much I am deviated from this L star, which is the unique arm that is preferred by agent J under collision. Okay, so we are after this regrade of agent J. Good. So now, so what are some of the strategies to address this kind of multi-agent, multi-arm bandits? So typically in bandits also we use UCB type techniques and we use some explore and commit type techniques. So let's first look at UCB type techniques for a competitive bandit setup. So I'll just give a very brief summary because this is not a part of my contribution, but in order to make the story consistent, and since this is not standard area, I thought maybe I should include one slide, but people usually do in this set. So this in the UCB based algorithm, there is this algorithm called UCB D3, which the idea here is to play UCB on a restrictive set of arms. So we just saw that if I pull an arm that is preferred by agent higher than me, rank higher than me, I will get determinants 0 to 1. So I will avoid that arm, right? So this algorithm actually constructs some active set, right? So it estimates the arm that is played by agents higher than it, and it tries to not play that arm. Okay, so it constructs some active set and play UCB over that active set. So that's in a nutshell what UCB D3 is. Okay, so the ultimate algorithm is an epoch-based algorithm where it will first estimate its rank, and then it will estimate the arms that are preferred by the higher ranked agent, and it will try to avoid that. Mean that it will remove those arms and play UCB on the remaining set. So this is what people typically do. So I haven't started talking about our problem yet. So it can be shown that this achieves logarithmic. On the other end of the spectrum, one can think of explore and commit type algorithms, where the idea is you will explore and you will collect samples based on this some round robin tournament, and then you will construct this LCB and UCB indices of the arms. Okay, and you say so for some agent, let's say agent prefers arm L1 over arm L2 if the LCB of arm L1 is bigger than UCB of arm L2. So these are all very standard things. So now the idea here is I will do this explore and commit, and I will estimate the preference based on this kind of condition, and then I will so after this preference is learned, I will play Gaussian. So I will explore, collect samples, estimate the preference based on this condition, and then I will play Gaussian. So that's the explore and commit type algorithm for temporary dynamics. And these are collision-free algorithm. So there's no collision. So yeah, so people typically try to avoid collision because if you collide and you are not the chosen one, you will get deterministic 0 reward. But if you play some suboptimal arm, you will still get some reward. So so the idea, general thinking process is that you should design an algorithm that avoids collision, because if you are not the chosen one, you will get 0 reward in that round. So that's the idea behind this strategy, the idea behind the design of our algorithm as well. Now, whether this strategy is the best one is debatable, but this is a strategy. So now we are going into the main part of the talk. So so these previous works, they consider static market, meaning that these arm preferences, they don't change over time. Okay, but markets are not stationary, right? So it depends on the day of the week or the hour of the day or whatever, right? So so this studying dynamic markets is actually an active area of research. And in this works, people typically assume that they know the preferences and they try to model the behavior in future, and they try to come up with algorithms, right? So our goal is to propose a bandit algorithm in the competitive market setup under dynamic markets, for dynamic markets. Okay. Please feel free to ask questions, clarification. Yes.
So, here the agent ordering is known.
Yeah. So the ordering is, so we will throughout assume that the agent ordering is known. Okay. So it's, yeah.
I'm guessing it's coming. Do you make assumptions on the how dynamic the market?
Yes. So so there can be multiple models how to capture this non-stationarity in multi-arm bandits, right? So this slide is just a quick review for that. So we all know that this UCB will not work if we use it as is in a non-stationary market, right? So you have to use some sort of window-based UCB or discounted UCB, the classic paper by Olivier Garibia in 2008. and there can be different types of changes. This environment can change slowly or abruptly, right? So you have to design algorithms tailored to change of the environment. Or there are papers that assume a total budget of change. They don't care whether the change is slow or abrupt, right? So as long as the total budget is known and it changes within that budget, you are fine. Okay, so there are paper by ZV and Vesdes on that. So very recently, so our very own Adit is not here. I think the student proposed an algorithm that deals with this kind of very slow changes. So it means that if we go from time t to t plus 1, then the total change is upper bounded by some number delta. So this is called a smoothly varying market or a slowly varying market. Okay, so we will actually take this kind of assumption for like the dynamic market, and we'll propose algorithms tailored to this kind of change. Okay. So we can define the regret analogously. So the only thing is now everything is time dependent. So this unique stable match will also have a temporal component. So we can define the arm preferred by all the agents and the unique stable match as a function of t, and we can define a regret accordingly as well. So the only thing is you have another component t that you need to take care. That's it. Okay. Good. So to that end, we propose this algorithm called a non-stationary competing bandits. Okay. So we'll first use, I will explain what is called a Symbolic algorithm. Symbolic algorithms of Krishnamurti. So Symbolic basically says that you are working in an environment where the R means are changing. So the idea is you need to do explore and commit type algorithm, but successively, right? So you can't say that I prefer this arm, I will play it indefinitely. That's not possible because R means are changing, right? So you do some exploration, you say that this arm I think will be optimal for the next few rounds. So you fix on that arm, right? Now you explore again and commit again. So this successive exploration and exploitation kind of thing typically works for a slowly varying market. Now if the change is abrupt, this kind of thing will not work, right? So this is only this is an algorithm tailored for just slowly or smoothly varying values. Okay, so now so the thing is we can't just use this very simple algorithm and extend it in the multi-agent case because we need to respect these competitions, right? So there are rankings, so we need to avoid certain arms that are preferred by agents ranked higher than me, right? So it's not like a very simple extension. We need to do some work around it. So for example, one can think of this a very simple two-agent system. And for agent 1, there is no competition because agent 1 is the highest ranked agent. It will just explode and commit successively. Okay. But for agent 2, let's think of a situation where the instance of agent 1 is hard, meaning that let's say the minimum gap between the arms of agent 1 is much smaller. So it will take more number of rounds to select which arm is the best. Okay. And suppose for agent 2, this instance is easy. So there is a huge gap. So it will just need very few cycles. But so but we can force agent 2 to continue the exploration because if agent 2 starts exploiting, then it will face collision in every k rounds because agent 1 is exploring, right? So one way to avoid collision is to just ask agent 2 to explore forcefully. Okay, so this is I'm just trying to avoid collision. Yeah. Because the arm means can be different, right? So arm means are indexed by I and J. So for each agent, you have a set of arm means, and that vector will change from agent to agent. So it is certainly possible that for one agent the instance is hard, for the other agent the instance is easy. So this mean has two indices, the agent and the arm.
Consider that for using the answers, the ranking of answers.
The ranking is different, but throughout this we are assuming that this arm mean is mu I j T. So it has 3 indices. So this mu's are different for different agents. So that is the assumption throughout. We are not removing that. That will make the problem very easy. So yes.
I think the question is, you had started out with an ordering, even though the mu ij t.
Yeah. So now I'm talking about mu ij for the ARM side.
So the ordering is not preserved across the users.
Yeah. Any other questions? So, so you can see that since agent 2 is not ranked higher, agent 2 is forced for some amount of exploration, right? And also in the flip side, agent 1 will take longer time to explore and shorter time to exploit, right? Because the instance is hard. But agent 2 might exploit for a longer time. But as soon as agent 1 starts exploring, we will force agent 2 to start exploring as well. Otherwise, agent 2 will face collision in every k rounds, right? So in a way, we are trying to avoid collision and we are trying to force agent 2 for forced exploration and restricted exploitation. Now, this is a sufficient kind of argument, right? One can say that, oh, I can handle 1 collision in every k. I can still get something out of it, right? So, but it turns out that this kind of collision-free algorithm will lead to a nice algorithmic design with regret guarantees and all. But right now it's kind of unclear whether we can allow collision and we can still get some very nice results similar to what we got in this paper. So as I said, so it's not clear whether this is the best thing to do or not. Okay, so let's look at the algorithm. So we'll actually characterize a regret of a system with 2 agents, just for simplicity, and we'll very soon see that this framework can be extended to an n-agent system by a simple inductive argument. So it's sufficient to just understand complexity of the system for 2 agents. So let's do that. So the first, sorry. So the first phase of our algorithm is rank estimation. Okay. So initially we don't know the ranking or anything. So the idea is by the end of this phase, every agent gets to know its own rank. So agent rank 5 will know that I am rank 5. I don't know about the ranking of other agents, but I will know my own rank. So that's the goal. And this is accomplished in the following way. So in the first instance, I will let all the agents pull on 1. Okay. So now the reward will be given to the agent ranked highest. So the reward will be given to the first agent, right? So now for p equals 2 to n minus 1, the agents who already got a reward, aka the agents who are already matched, they continue to play the arm it matched to, and the other agent will play arm index t. Okay, so think of a very simple system with 2 agents. So both agents are pulling pulling arm 1. So the first agent will get the reward. Right, the first agent knows that okay, I got the reward in very fast round, so I am rank 1. So agent 2 will get 0 reward. Agent 2 will immediately say that I am ranked. Okay, similarly, if you have 3 agents, the same kind of argument goes. So at the end of this phase, everyone knows their own rank. Okay, good. So any issue? So this is just an inductive argument. You can think about the collision structure in your head and just think of very simple systems with 2 agents and 3 agents. You can use this inductive argument to say that everyone knows their own rank. So this is done. Everyone knows their own rank. Good. So now let's look at the action of agent 1. So as I said, agent 1 faces no collision. So it will just use the Snowzit algorithm or successive exponent commit type algorithm. That's it. Okay. So yeah, told you that since the armings are changing, it's not sufficient to do once, you have to do it multiple times. There's no competition, nothing going on. So let's be a bit more formal. So I will explain the test that agent 1 performs and based on which it commits. So the idea is all the other agents will also perform the same test, but let's define it for agent 1. Okay, good. So let's assume that mu hat ATW tilde is the empirical mean of arm A at time t based on its last W tilde pulse. So we define this lambda optimality, lambda A optimality in the following sense. So you are given a set A. So you say that arm at time t, some arm A is lambda optimal if there exists some lambda tilde such that the LCB of arm A is bigger than the UCB of arm B with slack. Okay. So if I just put delta equals to 0, this is just LCB greater than UCB kind of argument. Now, so what is this set A? So we can define the optimality with respect to a set A. Now this is not required for the rank 1 agent because rank 1 don't care about other agents. It has all the arms from which it decides which arm is optimal. But for rank 2, rank 3, rank 4 agent, so it has to like delete some of the arms that is preferred by the higher rank agent. So for them, this definition makes more sense. But let's define it formally for agent 1 also. But for agent 1, A is the set of all arms. Okay. So this definition is clear. So it's just saying that agent 1 will say that arm A is optimal if the LCB of arm A is bigger than the UCB of all the arms in the set over which it is deciding the optimality. That's all. And you have slack. Okay, great. So now once such an optimal arm is found, this the agent 1 will exploit that arm for some number of times. And this number is actually determined by the fact that like based on the gap and all, you can show that this in this interval the regret of playing such an optimal arm is 0. So once you find an arm, you want to come up with the length over which that arm will remain optimal in this definition. It turns out that this is the equation. So for agent 1, it's very simple. It will just perform this test and it will exploit for this amount of time. Success is done. Okay, so yeah, so this is another component we have. So it's called a blackboard communication model. So since this is a decentralized platform, there is no center to kind of broadcast message from one agent to other. So we assume that there exists a blackboard where agents can write limited information and this blackboard can be seen by other agents. So this is not as strong as existence of a centralized server or a centralized authority, but we'll just make the assumption that some information can be broadcasted through the blackboard. Okay.
So here you're having the agents provide this information.
Yes.
But taking a cue from game theory, there are these correlated mechanisms where you can have common randomness, which is like today's newspaper, for example, which is accessible to everyone. So would that be an intermediate one?
Yes, yes. So yeah, if you have that kind of setup, then this kind of assumption is not as strong, right? So this is kind of already embedded in the system.
But this requires an agent to write.
Yes.
Whereas in the other one, it's just common randomness.
It's just common knowledge to everyone. Yeah.
Okay, please.
Yeah.
We can discuss this.
Yes. So I mean, in cases where you don't have anyone to kind of communicate your message to the other agents, or if you are trying to solve a system which is decentralized, you need some form of communication, some mode of communication, right? And Blackboard is one such mode. And people in distributed optimization, they use this a lot. So in previous papers, they actually achieve communication through something else other than Blackboard. For example, in Shankaraman et al., they achieve this communication through what's called a structured collision. So they have this phased algorithm and they reserve some time for structured collision. And collision is informative, right? So if you collide, you know that you are ranked lower than some other agent and all. So this is not as simple as what they do, but the bottom line is they achieve a black hole communication type model through like communication structure through structured collision. Yes.
So will you preserve the order plane in the black hole?
So yeah. So in a minute I will actually explain what agent writes exactly in the black hole. That will answer your question. And also in the explore and commit type algorithm, they do it through some assumptions. So that's, I guess, the best way of achieving something. Just assume that things are being broadcasted. So that's also fine. So since we don't allow collision, of course, this statement is debatable. Why not? But since we stuck with the no collision algorithm, so we need something to communicate, and Blackboard is one such model. And we first get our results through this Blackboard, and then we'll come up with a heuristic strategy how to remove the Blackboard. Okay. So now the competitive part. Let's look at the algorithm for the second agent. So it will bring the competitive nature of the market, right? And as I said, the goal of agent 2 is to avoid collision. Now we'll see different scenarios of agent 2. So based on the activities of agent 1, there can be multiple situations of agent 2. So let's look at those situations. So in scenario 1, so suppose agent 1 explores and then commits to an arm. Okay, and the explore time of agent 1, let's say, is smaller than that of agent 2. See, it can happen when agent 1 has a problem instance, which is easy. So now, what will happen? So when agent 1 starts committing to a particular arm, agent 2 will simply avoid that arm. So up to that moment, it will explore all the arms, but after that, it will just all the arms except the arm committed by agent 1. That's very simple, very heuristic. That's one should do intuitively, right? Let's look at a different scenario where agent 1 commits to a particular arm, and agent 2 will start exploring. It will explore all the arms except the arm committed, and it will commit to some time, right? So now suppose the commit time of explore 2 is off, so it will start exploring again, but agent 1 is exploiting, so it will just explore all the arms except the arm committed by agent 1. So I'm just trying to come up with situations where agent 2 will either face some forced exploration or it will face some restrictive exploitation. Okay, so these are the two situations where either agent 2 faces domination via restrictive exploration or domination via commitment to a dominated set of arms. Right, so it can't commit to the arm it wants. Right, it will only commit to arm that is available to it. So this is just agent. Think of agent R. It needs to avoid all the arms preferred by all the other elements. We'll talk about that. So there can be some other situations as well. So I talked about this forced exploration. When agent 2 has like a very simple system, it can't commit because agent 1 has a complicated system. So it will depend on agent 1's gap and everything for this kind of forced exploration and all. Okay. And also agent 2 might have successive phases in one total explore and commit period of agent 1, but it needs to avoid the arm that is preferred by agent 1. So it can't explore or commit the arm I that is being committed by agent 1. So bottom line is like you need to respect the arm committed by the agent ranked at the okay. So all these things can be written down in terms of an algorithm. I don't expect you to read the algorithm, but the main idea is you can either so the agent 2 can either explore all the arms. If agent 1 is exploring, there is no issue. So it can explode all the arms except the arm that is that is being committed by agent 1. So this is explode minus J, or it can exploit. So while exploiting, it will perform this test on a restrictive set of arms, right? So now you need to delete the arm that is being preferred. So it will do the same. It will come up with a buffer, and also as we saw that you need to end your exploitation as soon as the agent rank higher than you starts exploding. So there's a restriction here as well. There's a lot of restriction that agent 2 faces. And this is by design. Of course, you can say that I can come up with another algorithm with collision with a better analysis. But if you try to avoid collision, you can come up with this algorithm, and we'll show that this will give you a regret which is still logarithmic in T. But the dependence on the problem instance gets worse because now you need to depend on action of agent 1. So the gap or the complexity of agent 1 comes in the regret as well. Okay, good. So so now we'll try to define the regret, and you need the complexity gap or the problem dependent gap for that. And the gap definition is same as like a standard multi-arm bandit. The only thing is, instead of characterizing it for a particular instant, you will take the average over a window. Okay, so average gap between pairwise arm means over a window. So this may look complicated, but it's exactly the same thing as people do in multi-arm bandits. You just take the average over the window. That's it. Good. So you're right. So you can define this dominated set, and you can define the complexity over a dominated set. So basically, you are trying to find the minimum gap between the arms in the set of all the arms minus the dominated set. Basically, for arm 2, so the dominated set is the arm index, arm of player 1. It will just remove that, and it will find the dynamic gap from the rest. That's it. So definition, everything is the same. The only thing is this is the new component, and this averaging is the. So this comes because system is heterogeneous, non-stationary. You need to respect that, and this comes because there are certain ranking in the system. You need to respect that as well. Okay. So now let's look at the regret guarantee. So for agent 1. So the regret is same as the successive explore and commit type algorithm. There is no competition going on. So I will define exactly what this is, but the regret is still logarithmic in T, and it only depends on the gap of agent 1. So lambda mean. So for now, let's remove the mean. So lambda is, let's say, some complexity of agent 1, and this thing denotes the agent. So this is the gap of agent 1, and it only depends on the gap of agent 1 because it is the highest ranked agent. But in contrast to that, for agent 2, it depends on the complexity of agent 2, right? It also depends on the complexity of agent 1, and it also depends on the complexity of agent 2 on the restrictive set. So we'll define all these three things. But one thing to notice is that since we have forced exploration and restrictive exploitation, it's obvious that some extra regret should be incurred by agent 2, and that should depend on the complexity of agent 1, right? Because while explaining the forced exploration, we say that that will happen only if agent 1 has a very complicated system, while agent 2 has a very simple system. So this is saying that even though agent 2, the gap is bigger, if agent 1's gap is small, then you get impacted by that as well. Yes. Agent 2 is? Sorry, I don't know.
It's possible agent 2 start. Agent 2 start. Is that right?
Yeah.
So what is meant by start? So by design of this algorithm, that will never happen, right? Because I'm always trying to avoid collision, right? So by definition, I will avoid the arm preferred by the agent rank higher than me. In this case, the first rank agent, right? And then I have the flexibility to. You have sufficient arms. A is bigger than N. Ranking is same throughout, yeah. So the ranking in the left hand side is same throughout. The ranking in the right hand side is changing over time.
But I think there's a point there. Because
Yeah.
lambda mean value 1. If it is the difference for the first agent is small, and the first agent is
Exploring a lot.
and that could lead to possibly a lot of waiting. Even though there is no
Yeah, yeah.
collision, there's still waiting.
Yes.
Learning is impaired for the second.
Right, exactly. So that's exactly the case, right? So that's what we call forced exploration. And it turns out that extra exploration is upper bounded by k log q over this. So yeah. So now, so this lambda mean is the minimum gap over a certain over a block with certain length. That's fine. But we'll just explain these three terms in the regret of agent 2 now. So for agent 1, I think it's clear that it will depend on the complexity of itself. For 2, we have three terms. So the first term, we all understand this first term 1 over gap is coming from pure exploration. So if it's exploring all the arms, explore all phase, you have this 1 over lambda p. Same as the first agent, right? Now this is there. The second term, as you said, comes from forced exploration and restrictive exploitation, because either it gets to explore a lot or it gets to forcefully end its exploitation. So the regret incurred by the agent will be much larger than what it should be, right? And that will depend on how complex the problem of agent 1 is, and that's exactly this term. Okay. And the third term actually comes when the agent is exploring all the arms minus the arm that is that agent 1 is exploiting. So it's exploring all but j. So for that, it depends on the gap of agent 2, but you need to remove the arm that is cleared by agent 1. Okay, so it's a restrictive dynamic gap, and the restriction comes from the commitment of agent 1. So it has these three phases. There's this regret coming from these three phases. And during exploitation, no regret. So regret is only during exploration. So you design the length of exploitation period in such a way that there is no exploitation. There is no regretting. Okay, by the way, this regret actually matches, although it looks very odd, it matches the standard regret when we have no non-stationarity in the system. Okay, now that was for 2 agents. We can extend this for n agents using an inductive type of argument. So let's first look at the algorithm.
So the matrix in the sense of log p, the constants are.
Yeah, the constants may be different. So now, for the n for n agents, the algorithm is as following. So at every time the agent ranked R, it will look at the blackboard. Okay, and I will allow every agent to write the following statement in the blackboard. So the agent will write that I am agent ranked, whatever the rank of the agent is, and I am committing to this particular arm for the next this many rounds. So it will write that information. Okay. So all the agents will write that information, and if agent rank R looked at the blackboard at time t, it will get to construct this set CTR, which is the set of committed arms by agents ranked higher than it. Okay, so it knows the information, so it will construct this set, right? Good. So now once this set is constructed, then the agent will either explore minus CT, so it has the set of all arms, So it needs to delete the arms that are being committed by higher rank agents, and it will explode within the rest. So that seems like very like intuitive. That's exactly what agent should do, right? So either it will explode or it will exploit. Now, when what is the condition under which it exploits? So if the cardinality of this CT is r-1, means that if all the agents run higher than you are committed, then only you get to commit, right? So if someone is exploring, then if you commit, then you will hit collisions in every k rounds. So we are putting much more restriction on the higher agents. So it only gets to commit when all the agents higher than 8 is committed, has committed to some arms. Then this is exactly similar to the 2 rank agent, right? Agent 2 gets to commit only when agent 1 is committed. So agent R is some restricted exploration and also forced exploration as well. So the same argument holds for R for any agent, but it becomes very cumbersome. So it's good to get some insight for 2 agents. Okay, so yeah, I will not go through it obviously. So it will either explode. So it will first estimate this set. So if this set is just null, it gets to explode everything. And if the set is something other than the null set, it will explode those set of arms, or it will commit. And while committing, it will perform the same test on a set while subtracting the arms, the set CTR. That's so whatever we did for the second agent, you can do the same thing for the RH rank agent seamlessly. And after doing all these things, it will update the blackboard that I am ranked R and I have committed to this arm and I will exploit it for the next this round. That's it. So the analysis is actually very simple. One can use simple inductive argument. So agent rank R can just look at agent rank R-1, right? And this is the sequence of a two agent system. R-1 will just look at R-2, R-2 will look at R-3 and all, right? So this is obviously a sufficient condition, and this is a regret upper bound. So the regret of agent R will depend not only on the gap of agent R, so it will come when it's exploring all the arms, but it will also depend on the gap of R-1. Now gap of R-1 will depend on R-2, R-3, R-4 successively. So the regret of agent R will depend on the complexity or the gap parameter of all the agents above it, which makes sense because I am performing some action based on the actions of previous agents. So I'm respecting their rank, and hence I'm getting hit by additional regret. And that is not impacting the tail of the path, that comes only in the problem complex. Yeah, this is exactly what I said. Okay, so now we can think of removing the blackboard, right? So we have some results without the blackboard as well, but so we will talk about that in a minute. So let's focus on a simple system with n equals to 2, right? So with blackboard, agent 2 knows whether agent 1 is exploding or committed to a particular arm. So that's the only information it can get from a blackboard. Now my job is to design a mechanism such that I get the same information without the blackboard. Okay. So suppose agent 2 maintains a latent variable qt and updates it successively, and let's say at the beginning q is explode. Okay. So now let's look at this very simple case. So when agent 2 faces a collision, let's say on arm J, okay. So either two things has happened. Two things happened. One of these two things happened, right? Either agent 1 has ended exploration and it has committed to arm J. So in that case, agent 2 will face a collision on arm J, right? That is one possibility. The other possibility is agent 1 has ended exploration and it's exploiting in a round robin fashion, and it will get hit at arm J. So these are the only two possibilities, right? So is this clear? So when agent 2 faces a collision, either of these two can happen. So there can't be anything else. Either agent 2 has committed or agent 2 has ended exploitation and it started exploding. Good. So now I can just look after collision. So agent 2 will look at QP minus 1. Okay. So if QP minus 1 is explored, right? So if QP minus 1 is the state of agent 1 at 5 units per second. Yeah, I'll end it before that. So if QP minus 1 is the state of agent 1 at T minus 1 instant, and if that is explored and there is a collision at time T, so of course agent 1 has ended exploration. Because I know that in T minus 1 it was exploding. So it's true that this A has occurred, right? And if QT minus 1 is exploited, meaning if agent 1 was exploiting, so obviously agent like this B has occurred. It must ended its exploitation and started exploding. So if I just assume that Q1 is explored, and if I just toggle this Q, whenever I face a collision, I get the same information as the blackboard. I don't need the blackboard, right? So whenever I face a collision, I'll just look at this and I can infer these two. So it's the same job as a blackboard. In a simple system, I can remove the blackboard very easily. And for general N agents, you need another latent variable, but the same argument can be done. And whatever results we have shown can be extended to learning without blackboard for a lambda, for a delta, which is a change parameter, for a much smaller delta. So suppose we have a system where delta is some number, let's say 10 to the minus 2, right? So right now we can take that system, we can map it to a system without blackboard, but the delta that it can tolerate is much smaller than the previous. Okay, so that's another weakness. But we're working on that. But the main idea is whatever I presented today in the presence of a blackboard, then that can be the same arguments will continue to hold without the blackboard with some additional modifications. That's it. And in our paper, we actually talk a lot about its modifications. Okay, good. So we also have some simulations, and this is matching whatever we thought. And yeah. So one reason why I chose this problem is because like this is a relatively new problem, and there are like a lot of open problems in this area, right? For example, we only consider these very smooth changes, right? And right now we don't know anything about this abrupt change and all. So obviously this successive explode and commit type argument will not work there. That only works for slow changes, right? And also beyond serial leadership, we don't know what to do right now. And yeah, so one problem that is bugging me from day one, started working in this area, is this assumption of one-sided learning. So we kind of assume that these arms know the preference, and we only learn the other side and do a lot of stuff with that. But this fundamental problem of one-sided learning without centralized agent is still an open problem. So in this new IISc, so we had a couple of papers that, like, via the virtue of several assumptions, they kind of convert this problem to a one-sided learning problem, but they claim that that's a two-sided learning paper. But though, if you ignore those kind of papers, this problem is still open. So yeah. And so yeah, so very recently we proposed a very simple just explore type algorithm for a two-sided learning problem, but it impacts some terrible regret, and that's why we are still learning. We are still working on this problem. And also this multi-agent, multi-arm bandits, in presence of competition, it's not unreasonable to assume that there might be some adversaries in the system who are trying to make things deliberately bad, right? So how do we handle adversaries? We know how to handle adversaries in multi-arm bandits. So there is this algorithm called Barber and many others followed from that, which handles adversaries in a nice and elegant manner. But we don't know what happens if we have more than one agents with competition. And also, this is for simple bandits. So if we have some structures, let's say linear or contextual, so can the same argument continue? We know that UCB can be extended to linear UCB without any effort. So from the same argument, can I use like restricted UCB to restricted linear UCB? So it turns out that the simple extension doesn't work. So if it worked, I would have done it, but we need some additional work. So whatever I talk today is actually taken from this paper. This paper and this two-sided learning is also something I am quite interested about. And this whole area is of interest to me. If someone wants to talk, someone wants to work on this area, they are welcome to contact me. And with this, so all these papers are also available online. So with this, I will conclude. Thank you.
Is there a way by which we can have a little more light? Questions?
When you convert it into a non-Blackboard problem, it's like solving one particular variable seems like a Boolean variable.
Yeah.
That would be sufficient.
Yes.
To clear all the confusion. It's supposed to be updating the Boolean.
So that is for agent 2. So agent 2 maintains it. It starts from some explore, and then whenever it faces a collision, it just toggles it. It takes two values, explore and exploit. That is the phase of agent 1. It starts with explore. Whenever it faces a collision, it will just toggle it. So it keeps that value updated in, like internally, like it's not broadcasting that, or there is no centralized communication going on. It can do that on its own without the value.
Yeah, go ahead.
So you consider that each agent has an arm, like wheel is being set or the arms. So those are the means of some stochastic distribution corresponding to that.
Yeah.
So when you have a collision, you give 0 to all arms.
Right. I know where you are going. So if you have a Bernoulli reward, it's not easy to identify whether it's from the reward distribution or from a collision, right? So right now, all these words kind of assume that you are working in a continuous reward framework. So it's think of like uniform or any continuous distribution bounded, let's say. But if you have Bernoulli, that's also an open problem, by the way. So yeah, I don't know. That's the easiest answer.
I have a question. So I think one thing that your removal of the blackboard strategy does is it answers to some extent partially the question that I had asked about perhaps a common randomness that can enable some sort of coordination. You can't beat what you have because you can do it by achieving coordination without any external signal. However, those constants, etc., do you have some idea as to whether they are optimal, and maybe some common randomness can help improve those constants? Usually, if you look at the Lie-Robbins framework, there is the constants are tight when you have
Yes.
some sort of information theoretic lower bound matching these achievable ones. Usually one does the lower bound and then comes up with achievable strategies. So any thoughts on the constants and
Right. So
how far away these are from the object?
yeah. So right now, like so I haven't explored that route yet, but I think like so the improvement. Sorry. So the increase in regret that we currently get from a blackboard to a non-blackboard system, it's not just in terms of constant, it's also on a dependence, it also depends on the number of arms. So so you can show that the delta that you want. Yeah.
We are looking at let's say a fixed k, and then you're looking at the
Right. So
at the constant.
then the constants make sense. So yeah, we are kind of not very faithful to the constants in this work, but I'll definitely look into how to improve
Just
the
a curiosity,
constants.
yeah.
Yeah.
Any other questions from the audience? Okay, if not, let's thank Abhishek once again for his talk.